we will present you not the next step, because the first step regarding the recycling of composites and FOD panels was to dismantle the composite from the titanium layer with laser shock. Then you obtain composite and titanium, and for the composite, what was the aim of the task for Comet is to explore the possibility to recover carbon fibers from those composites. Okay, and I will explain. I will start first with my company. Why? It's because recovering carbon fibers isn't easy, and but recycling companies should tackle those, let's say, new feedstocks to be able to recover and to recycle waste from aeronautic waste. So Comet Group, it's a family group, mainly located in Belgium, and you see that we are 500 staff and 500 million euro turnover. It's a recycling company with shredding sites, with a shredder located in Mons, that is the biggest one located in EU 27. We process more than 1 million tons of waste per year, and mainly metallic ones. So the main waste feedstock are end-of-life vehicles, electric and electronic equipments waste, but also demolition waste, etc. So what do? We are dismantling first, sorting the waste, and then shredding. And the mother company, Comet Sambre, is with a magnetic separation, exploiting the ferrous scrap stream, and is the main and is active in the steel industry. Then after shredding, you have shredder residues, and that is the job of Comet Traitement to exploit. And the aim of Comet Traitement is to focus on, let's say, obtaining at the end secondary materials as close as possible as the virgin ones. So we recover non-ferrous metals, plastics, minerals. And so it's very important to understand that the value of the material we can sell increase with the purification and sorting technique. So now we face more and more new feedstock. So one big issue is the mobility, the new electric mobility with electric cars, e-scooters, and so on. We are also active now. We are very active in research and development to develop pilot scale demonstrators and plants to process those wastes. And so we have invested in research and development to handle also photovoltaic panels. You see the next picture is part of aircrafts. So today we investigate also the activities in this field. And the last one is wind blades. All those waste needs to be processed, and with many challenges, and in particular from the battery side for the electric vehicles, fire issues. Okay, so now I come to Morpho project and our role in this project, and it was to recover carbon fibers from aeronautic composites. And so the idea is to remove the resin without affecting the carbon fiber and assess the feasibility of the process. So you see a picture here, okay, from a scientific paper where you have different steps. You have the pyrolysis step. Pyrolysis is a process to heat the material at high temperature without oxygen. And this process enables to remove the resin from the composite. but there is still some resin on the fiber. And the next step is the oxidation to remove this resin and to obtain carbon fiber without resin. So 2 steps, pyrolysis, then with a range of temperature to define between 400 degrees and 600 degrees. And then oxidation with 5 to 600 degrees, typically. So what we haven't done in the project is the next step to obtain the resin and then transform them in new composites. I think that the next speaker will elaborate a little bit more on these aspects. So why was Comet invited in this project and was active? Because at Comet we have installed a pilot scale demonstrator, a pyrolysis plant pilot, that was initially developed for organic shader residue. When you have residues from, for example, cars, you have foams and so on. And the idea was to develop this pyrolysis to pyrolyze the foams to obtain, let's say, fuels and energy. And this plant, this pilot, was adapted for morpho to the plastic composite material recovery. So what is the methodology? The methodology was first to start from a virgin carbon fiber and to characterize this fiber, then to compare with recycled carbon fiber. So the first part of our work was to perform lab scale trials in glassware and tubular oven with pyrolysis and oxidation trials to deduce the optimized time and temperature for pyrolysis and oxidation. Then characterize the recycled carbon fiber to obtain the optimized parameters. And it is an iterative process. Then we did it on semi-industrial level. So we'll pass now the floor to my colleague, Xavier.
Okay, hi everyone. So as it was explained on the previous slide, the method consists of first performing several tests on lab scale and tests just after for the upscaling. So we use 2 different types of reactor on the lab scale. So you can see on the left side the glassware reactor and the right side the tubular oven. So the advantage of the glassware is that we have a good flexibility to modify and to adjust the parameter, like temperature. You can put a probe on different place. You can also have a look on the temperature of the vapor, on the liquid, and you can easily adjust the temperature of the test if you want. For the tubular oven, that is quite the same characteristic, but we can increase the temperature compared to the glassware. Another advantage to the glassware is that you can directly see what happened during the process of the pyrolysis. Then, when all these tests were done, we directly go to the pilot. The pilot is a bigger reactor, so we can put inside more materials. And for this one, the quality is the advantage is that we can get data like heat balance, because we can put more material inside. So because the recovery of composite was new for us, what we have done is first have a look at what it is wrote in the literature, and we decide to set limit of your study, and we perform test at always 500 degrees, but we test during 2 hours and 6 hours for the pyrolysis. And then for the oxidation, we try different residence time of coming from 0 minute to 60 minutes. With all this data for the lab scale, we get in data for the mass balance and also for the heat balance. And what we have seen is the oxidation allow to the recovery fiber to become more and more released. But we will see it in the next slide. So after the test, we made the characterization. So we made two kind of characterization, a microscopic one and then mechanical ones. So on this slide, what we can see, if you have a view of the virgin fiber, we can see that the fiber is quite clean. And for the rest of the image, we can see the fiber with the dirty and the resin remaining on the surface of the fiber. And more we increase the residence time of the oxidation, so coming from 0 to 13 and 16, and more we can see that the resin is removed from the fiber. That we can clearly see that the influence of the oxidation of on the surface of the fiber. But this phenomenon is we have to be careful with this phenomenon because we don't have to push too far the oxidation to avoid to cause damage on the fiber. So this one is a table with the mechanical properties on the fiber. So on the red one, we can see the virgin properties for different parameters like tensile strength, Young modulus, ultimate elongation, force maximum, and so on. And for the green one, we can see for the parameter we chose, so 2 hours of pyrolysis and 30 minutes of oxidation, the data what we get for the recovery carbon fiber. And that is clearly a success for us because we can see that we get recovery fiber with only 10 to 15% loss of properties compared to the virgin one. So that is really a good thing for us. Yes, that's it for the slide. When we finish with the lab scale test, we decide to transfer all the test to the pilot, and we start with a test with the Safran Belgium sample, and we get this recovery fiber. And what we can see on this recovery fiber, that the pyrolysis was good, but all the fiber was interlocked. So it was more difficult after to get data on this fiber, and we decide to continue test on the static reactor to avoid the interlocked fiber. So during the study, we made a lot of tests. So you can see that we perform more than 30 tests on different reactors with different parameters. So always for 500 degrees, but we change the residence time for the pyrolysis and also for the oxidation. So all the tests are different, and for all the tests we get more information to increase your knowledge about the recovery of fiber. And we succeed to recovery fiber using your pilot, and we can see that for 2 hours of pyrolysis and more of the time 30 minutes of oxidation, that we get fiber with always good properties compared to the version one. So the results are quite good, and we can be happy with this because we see that we don't lose so much properties compared to the version one. Okay. After working on small sample, we try to realize the same parameter on the big CRFP panel, and what we can see is the results are not so consistent. We clearly see a lack of homogeneity of mechanical properties on this one, because probably we have to take in account of geometric aspect, and it will be probably possible to recover this kind of piece, but we need more time and more tests to find the new parameter, because we think that the different aspects like specific surface of the material could influence the result at the end of the test. So what we can say is the tests that we made are really good and encouraged, but for this kind of panel, we have to investigate more to find the new parameter good to find and recover good panel.
Okay. So it leads me to the conclusion of this short presentation. Just also some words about the instrumented panels. This week we are performing today the last trial on instrumented panels, and the idea is to see if what we can recover from those panels, because instrumented panels means also sensors and inside, and so it will be very useful for us to see the exploitation of this technology. Okay, so the main conclusion. So we have got promising results at lab scale and to some extent to pilot scale on small parts of composite. So thermal treatment succeeds in recovering the carbon fiber with good mechanical properties. And what we need to investigate further is large composite parts, so the upscaling, homogenization of the pyrolysis temperature and so on. So results are not fully transposable today at industrial level. And we have also to have in mind that in the future, when we will get waste from aeronautic sector, we could face possible heterogeneity in real waste feedstock. So that was it for Comet. Thank you.